Hello and welcome to this session. In this session, I'm going to discuss the method of undetermined coefficients for the solution of the second order non-homogeneous differential equation with constant coefficients. Now, I'll start by defining what we mean by what we call a UC function. Now, a function f of x is said to be a UC function if it is defined by one of the following. Either is a polynomial of degree n, where n is a positive integer, that is, it can be expressed as x raised to power n, with n being a non-negative integer, either 0, 1, 2, and so on. Or it's an exponential function, e raised to power ax, or it's a sine function or a cosine function. A function which is defined as a sum or a product of two or more UC function is also a UC function. It is important to note that whenever you are given a UC function, the derivative of that function will also be a UC function or a constant multiple of a UC function. So if we have a function, say a function such as f of x is x raised to power 3, x to power 3, this one is a UC function. So if we differentiate this, we get 3x squared. So x squared is a UC function, and so the derivative f prime is therefore a constant multiple of a UC function, that is 3 times x squared. If we find the derivative, the second derivative, f double prime of x, then we get 6x. Again, x here is a UC function, so you can see that f double prime is basically a UC function, which is x multiplied by 6. So it's a constant multiple of a UC function. If you take another function, call it g of x, which is e raised to power, say, kx, or say 2x, and you differentiate g with respect to x, then you get 2 times e raised to power 2x. Again here, e raised to power 2x is a UC function. This one is multiplied by 2. So g prime is as a constant multiple of a UC function. So any UC function, given any UC function, the derivative would also be a UC function, which may be multiplied by a constant. Now, when we are solving a differential equation, a second order non-homogeneous differential equation using the method of undetermined coefficients, one requirement is that the function which is the function f of x here, because the function will be, the differential equation will be of this kind. The function f of x must be a UC function in order to use the method of undetermined coefficients. So let's now look at another definition. And suppose that a function f of x is a UC function. Then the set of all functions that consist of the function f of x and all its linearly independent functions which are successive derivatives of the function is known as a UC set. You are given a function. You are given a function such as f of x is equals to x raised to power 3. Then you differentiate this, you get 3x squared You differentiate again, you get 6x, and you differentiate the third time, f triple prime of x, we get 6, which we can write as 6 times 1. 1 is a UC function because we said a function x raised to power n, where n starts from 0 to 1 to 2 and so on. So x raised to power 0 is 1. So 1 is a UC function. So we can write the third derivative as 6 times a UC function, which is 1. So now here we can identify the UC functions. X power 3 is a UC function. 3x squared, we can drop 3 and say that x squared is a UC function. This is being multiplied by 3. 6, we have 6 times x. X is the UC function here. And then we have the UC function 1. So if we now identify the set consisting of all these UC functions, so we write the function 1, the function x, the function x squared, and the function x cubed. Now this set consisting of this function, we call it the UC set. We call this set the UC set. The set consisting of the function itself together with other functions that other UC functions arising by differentiating the given UC function. If we have a function, say g of x is equals to sine of say 2x, and you differentiate this one, you get 2 cosine of 2x. You differentiate again g double prime of x, and get minus 4 sine of 2x. You differentiate again the third derivative, and you get minus 8 cosine of 2x. So basically, when we differentiate a cosine, we get a sine. When we differentiate a sine, we get a cosine. So by differentiating the sine function, we'll get a cosine function. Differentiating the cosine, we get the sine function. So we do not expect, even if we go to the fourth derivative, we do not expect a new function here. So the set of different functions arising from the differentiation of this function, we have the function g itself, which is sine of 2x. On differentiation, we get the cosine function. We don't write the coefficient here because this is just a coefficient. The function here, the function we identify here is the function cosine of 2x. The next one is the sine, which we already have here. Then the cosine, which we have here. So we see that there are two functions. So this forms the UC set. Sine of 2x and cosine of 2x. If you take another function h of x, which is equals to, say, the exponential 3x, and differentiate this one, we get 3 e raised to power 3x. We differentiate again, we get 9 e raised to power 3x. And we see that differentiating this function will not produce a new function. The only thing that will be changing is the coefficient here. So we can identify the UC function here, which is e raised to power 3x. In the derivative, we have again e raised to power 3x, which is the UC function, multiplied by the constant, which is 3. The second derivative, we have again e raised to power 3x, multiplied by a constant, which is 9. So the UC set here, the UC set consists of only one function, which is e raised to power 3x. So in general, if we have e raised to power kx, the UC set will comprise of only one function, which is e raised to power kx. But if we have a cosine function, or a sine in this case, we'll get two functions here, sine and cosine. Notice that it is not any different even if we started with a function which we can call p of x as cosine of 2x, because p prime would give us the sine and p double prime will give us the cosine. So when determining the functions that arise from this function on differentiation, we would only see the cosine and the sine. So we would end up with the same set of functions having two functions, sine of 2x and cosine of 2x. So basically that's how we get the UC set. That's how we get the UC set. If we have a cosine function, we end up with cosine and sine function. If the function is an exponential function, the UC set will comprise of only one function, which is the exponential function. Now, given a second order ordinary differential equation, which is non-homogeneous, of this form: a d squared y by dx squared plus b dy dx plus cy is equals to f of x, where f of x is a UC function, then the particular integral is a linear combination of the elements of the UC set. So in general, we write that if f of x is an exponential function, remember, if f of x is an exponential function, f of x is equals to e raised to power x, then the UC set will comprise of only one function, e raised to power ax. So in this case, the particular integral is the linear combination of the functions in the UC set. There is only one function here, so we write yp is equals to k e raised to power ax. So there is only one function, which is e raised to power ax, so we multiply by a constant k. This is the constant to be determined. If on the other hand, the function is a cosine function or a sine function, if I have a cosine function or a sine function, then the UC set for corresponding to this, the sine or cosine, we have two functions, cosine of ax and sine of ax. So we write their linear combination, k1 times cosine of ax plus k2 times sine of ax. If on the other hand, the function is a polynomial of degree n, then there will be the set of functions starting with x raised to power n, x raised to power n minus 1, n minus 2, and so on, up to x raised to power 0, which is 1. So the yp is their linear combination, the linear combination of all those functions. So now, when you are given a problem, like you are told to find the general solution of the differential equation here, the first thing is to find what we call the complementary function. Now the solution will be expressed as a sum of two solutions, yc plus yp. Yc is known as the complementary function, and yp the particular integral. Now yc is the general solution of the corresponding homogeneous differential equation. So we find the corresponding homogeneous differential equation, which we can write as d squared yc divided by dx squared minus 5 dyc by dx plus 6yc is equals to 0. So we solve this. To solve this one, we need to find the characteristic equation. Lambda squared minus 5 lambda plus 6 is equals to 0. Then we make use of the method of the quadratic formula, rather. Lambda is equals to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So a here is 1, b is minus 5, and c is equals to 6. So when we substitute, we get two values. Lambda 1 is 3, and lambda 2 is 2. So we write the general solution. So for the particular integral, you notice that our function here, f of x, is equals to x raised to power 2. So the UC set will comprise of the functions x raised to power 2, which is the function f. When you differentiate, you would get 2x. So we identify the function x as the UC function. And then when you differentiate again, you get the constant. So we identify 1. So the yp will be a linear combination of this. So we write ax squared plus bx plus c times 1. So c, where a, b, and c are constants now to be determined. These are constants to be determined. So we write yp is equals to that. So yp is equals to ax squared plus bx plus c. Then we can differentiate yp with respect to x to get 2ax plus b. The second derivative is 2a. We now substitute here. D squared y by dx squared is 2a. The first derivative here is 2ax plus b. And yp is this function. So we substitute and simplify. Then once we simplify, we can equate the coefficients of the corresponding powers of x. Starting with x power 2, we identify this side we have 6a x squared, which must be equals to x squared. So that 6a must be equals to 1, and therefore a is 1 over 6. X power 1, we have this term. The other side we don't have. So meaning that the coefficient here must be 0. 6b plus minus 10a is equals to 0, and therefore 6b is equals to 10a, which is 10 times 1 over 6, sorry, because a is 1 over 6. And therefore, we can get b from there. B is equals to 5 by 18. Lastly, we equate the constant terms. 2a minus 5b plus 6c is equals to 0 because we don't have a constant term here. Then from there, we can determine the value of c. And remember now, our solution was yp is equals to ax squared plus bx plus c. So we substitute the value of a is 1 over 6, b is 5 by 18, and c is 19 over 1 over 8. Then the general solution, y is equals to yc plus yp. So we get the sum of those two, which is the general solution of the differential equation. Now, if the function is an exponential function, again, we can solve the same way. Complementary function. We find the roots of the characteristic equation. The complementary function is the general solution of the corresponding homogeneous differential equation. So first we replace here with 0. We get a homogeneous differential equation. Then obtain the characteristic equation, which will be 9 lambda squared minus 12 lambda plus 4. We solve that using the quadratic formula. We get the roots. Now, we get only one root here. So meaning that the roots of the characteristic equation are equal. If the roots of the characteristic equation are equal, then the solution is expressed as c1x plus c2 e raised to power lambda x. So we can substitute lambda is 2 over 3, and we get this solution yc. Now for the particular integral, now we have the non-homogeneous differential equation. Our function f of x is equals to e raised to power 3x times 5 here. So the UC set here has only one function, e raised to power 3x. And therefore yp, which we say is a linear combination of the functions in the UC set. There is only one function, so we write k e raised to power 3x. Then we can differentiate first derivative, the second derivative, then substitute back 9 times 9k e raised to power 3x minus 12 times 3k e raised to power 3x plus 4 times k e raised to power 3x. Simplifying this, then we get k is 5 over 49, and we substitute back, we get the solution. Then the general solution is the sum of the two solutions. The third case is when the function given there, the function f of x is a cosine function or a sine function. Again, we start the same way. We first find the general solution of the corresponding homogeneous differential equation. So just replace this function here with 0. Then get the characteristic equation. The characteristic equation is lambda squared minus 4 lambda plus 29 is equals to 0. So that lambda becomes minus 4, which is plus 4, plus or minus the square root of 16 minus 29 times 4. And we divide this by 2 times 1. When we work out this, we see that we get negative 100 here. The square root of minus 100 is 10i. So we have lambda is 4 plus or minus 10i divided by 2, which is 2 plus or minus 5i. The roots are complex, and therefore the solution will be of the form yc is equals to e raised to power alpha x, then c1 cosine of beta x plus c2 sine of beta x, where alpha is 2, alpha is the real part and beta is the imaginary part. So we get this solution. For the particular integral, we are now solving the non-homogeneous differential equation. Our function f of x is 4 cosine of 3x. So our UC function here is the cosine. The UC set will therefore comprise of two functions, the cosine of 3x and the function arising from the derivative of that, which is the sine of 3x. Now, yp is the linear combination of these two. So we write k1 cosine of 3x plus k2 sine of 3x. Once we have the function yp, then we need to differentiate and substitute back here in the differential equation. So we find the first derivative and the second derivative, then substitute back and simplify. When we simplify, we get this expression here, and we equate the coefficients. The coefficient of cosine of 3x on this side, we have 20a minus 12b, and this side we have 4. The coefficient of sine of 3x, this side we have 12a plus 20b. The other side is 0 because we don't have the sine meaning that the coefficient must be 0. So we end up with two equations in two unknowns. And now we can solve these two equations to get the values of A and B. So A is 5 for 34, B is negative 3 for 34. Then we substitute back to get YP. The general solution is the sum of the two solutions, YC plus YP. So basically, this is the method that we call the method of undetermined coefficients.